What is up, guys? We are back with another video, and this time we are talking about electric field. Now, I'm going to talk about where the electric field originated and where it comes from, and how it's related to Coulomb's law, and that's important because we basically use Coulomb's law to get everything else, you know. So, okay. So first, we said that if we have a bunch of point charges, or source charges, and we have this point charge here, Q, we want to know what's the effect that these source charges have on our point charge, right? And then we said that we can use the fact that Coulomb's law is obeys the superposition to say that, well, if we can calculate each force individually, we can get the total force, right? So we literally get every force that there is, and we'll be fine, okay? But let's think a bit harder about this. So this is a cool result, but let's actually extrapolate what we mean when we say this. So from this result, we can actually say that, well, if this is true, and as we say, we know this is true, so let's go a bit deeper into the gutters and see what this actually means. Sorry, that's a 3. Well, we defined Coulomb's law as follows. So it'll be Q1 over Q, and I'm going to actually write the constant with my my things here, because it's going to get a bit scrappy if everything's written nice and neatly. But we know the point charge stays the same, but the source charge changes every time, and so also the separation vector will change. It's not the same for each point charge, or each point charge and the source charge. So it's important to note that these will change for each one, okay? And so it will continue on, right? And what we notice is that there's some things that are constant every time. The Q, our point charge, and this constant, right? So what are we left with? We're left with the source charge. It's, oh, that's not the nice R, this is the nice R. We notice that we get this interesting and repetitive function right here. And this is really unique because what we're basically saying is that we can define a function from this. And ladies and gentlemen, I will not waste your time any longer. Here I have a function that depends on the position and looks something like this. Let me say Qi, I, for I equals 1. Ladies and gentlemen, here we are. This is known as the electric field. Now, taking this into account, remember what I stated right here. So, what I'm basically saying is that, well, this accumulation of forces that we have on the point charge, well, it can be rewritten as follows. Because remember, I use this in my electric field definition and this all in my electric field definition. So if this is my electric field, there's my Q, and this is the force. So a really important result is that the force is correlated with the electric field and this Q, the point charge. Really cool. Now let's dig a bit deeper into this. Okay, so we're back, and we did something. Now that I've got you an interest in the electric field, we basically know that the force and the electric field are connected. Now the electric field is a way to see what the effect is of these point charges, or these source charges, sorry, I keep on switching them. But what is important to note, and what is really important to note, that this really awesome electric field function does not depend on the charge Q. That's important. So basically what I'm saying is that if we have an electric field, which we'll later define more clearly, but let's say we have an electric field, its magnitude and all its functions don't depend on Q whatsoever. That's only the force that depends on the magnitude of Q. So let's say we have like a barrier here. No matter where the Q is, it will experience the same electric field because electric field does not depend on the magnitude of Q. However, it is dependent on R. So this is important. So we can see that E is a function of R. And if you get really far from these source charges, well, then you won't experience electric field that much because it is a distance-dependent function. And that's basically what we can say about the electric field. And we can also say that, well, it's linked to Coulomb's law. So we can get the electric field or we can get the force. They're interchangeable if we have because of this relationship. So we can really do some magical stuff with this. And next up, we're going to do a simple example where we use Coulomb's law and this relation here to basically find the electric field. So there are simpler ways of solving the electric field, and we will look into that later because this is a really cumbersome process. But first we have to see how we need to do it without it, because this is basically the most fundamental way of solving problems in electrostatics. So if we have this, we know it will work for a lot of functions in electrostatics. However, there are easier ways, and the easier ways come with a price. So when we get to the easier ways, remember that, well, they are easier. It doesn't mean we can always use them. So no matter what, we can know this is true, and we can always fall back on this fact that this relation is true, and that Coulomb's law will really get us out of the gutters if our fancy tricks don't work in the future. Okay, guys, so here we are. We've got a problem, and it's a problem out of Griffiths. I'll put it on the screen now. And basically, what we're going to do is, well, they are asking what's the electric field at this point, Z above two equal charges. And you need to be careful with these questions because they give a lot of hints in the question itself. We first know that both charges are identical, which is a great start. And from this, they are equal distance separated from our particle P. I've just set it up in the sense that the distance between these two is d, and then from here it'll be d half for both. So we have this link z, and our separation vector, due to the fact of how we set up the question, is the same for both. And this is crucial because we really want the separation vector to be the same for both, so that we can simplify our answer as far as possible. We don't want to make it harder for ourselves. So let's start by what we know about the electric field. Well, we know the electric field is something like this. And let's start with Q1. Does not depend on the points or whatever. Like the electric field is just going, right? And it does depend on R squared, R1. However, sorry, that's the basic R. We want the fancy R. Okay, so we did this for 1, okay? But because they are the same, they have the same R1, so we can add them together because the force is additive by superposition. We know that the electric field is also obeying superposition. And we'll have this, right, as our electric field. But due to the fact that these two are the same, and the charges are also the same, well, this makes our job significantly easier, because what's going to happen is these will fall away, and we'll leave us with a 2 here. Because they're additive, and that's so awesome, because now we basically just got a simpler version of our electric field. However, so we can't know Q, because they basically just told us that Q is a charge, but we still need to figure out what these are. So next up, we will have to define these separation vectors. So firstly, we know that we can define our separation vector as the square root by Pythagoras. We know it is z squared plus d over 2 squared. Okay, so there we go. And if we square this, we know that this just falls away, which is good stuff. But I'm cautiously keeping this and not putting it in the equation so far, because I still have something I need to figure out. So now, going back to what we know that we have the angles between these separation vectors and the distance is theta for both. So we can say that we have cos theta is equal to, well, z over fancy r. Okay, that's good. That's good news for us. So using this, we can substitute this into there, and we'll get the following. So we got the following. We got cos theta in there. Okay, and we know what this is. So we know what cos theta is, right? We know it's this. So what's basically going to happen is cos theta will be substituted with z over r. Okay, good news, because now what's going to happen is the following. So we'll have our final electric field will be 2 over 4 pi epsilon naught over q over, well, z, and this to the power of 3. Okay, so we can rewrite this because we know what this is. We found it by using Pythagoras' rule. So it'll be z squared plus d over 2, 3 over 2. And this is all in the z direction. So the fact that we got this in terms of z is important, because we could have just used this, right? But we really wanted it in the z direction so that we can define the electric field that is relevant to us. So we want it to be an electric field that can be used at the application of point P, and hence we use this cos theta term to really get the z hat direction, because the electric field that we want to know is in the z hat direction. We could have gotten it in like whatever else, but this is the most applicable form of the electric field, and hence we use it. So this is a problem from Griffiths where we basically used the electric field and the superposition and a bunch of like just good setup basically to get the electric field at point P. Now, later we will go into more of the intricacies of the electric field and also simpler ways of solving this question by using symmetry. Because here we use symmetry, but it still was a bit of effort. But later we'll use Gauss's law and really get to the bottom of things and have a lot simpler method of solving problems. So looking forward to it, and I'll see you in the next video.